In this problem, we have the graph of this nice complicated looking function where we have x squared minus 2 to the power 4, x squared plus 1 to the power 5. We want to find the coordinates of the local maxima and minimum. That just means maximums and minimums, that's just plural. And notice that they went ahead and they found the derivative for you. The reason why is you would have to use the product rule because this is a product right here. And then inside of each product rule, or inside the product rule, you'd have to do the chain rule on this piece, and then inside this piece you'd have to do the chain rule on this piece. So you're going to have to use the product rule and the chain rule, and you're going to do all that, and then at the very end you're going to be like, oh wait, if I actually want to find out when the derivative is equal to 0, I'm going to have to factor it. So they were very nice here, and they went ahead and factored it for us. So you don't actually have to find the derivative. They did that. We just need to set it equal to 0 and solve for x to get our critical points. So we're going to take each piece and set it equal to 0. So 2x equals 0, x squared minus 2 cubed equals 0, x squared plus 1 to the power of 4 equals 0, and 9x squared minus 6 equals 0. So you put each piece equal to 0, solve for x. So let's see, this will be x equals 0, and then over here that cubed doesn't actually matter. You take the cube root of both sides, but cube root of 0 is still 0. So you get x squared minus 2 equals 0. X squared equals 2, x equals plus or minus square root of 2. Okay, and that is about, I think 1.71. Nope, I remembered incorrectly. It's 1.41. So it's about plus or minus 1.41. Okay, now we have this fourth root. We'll take the fourth root of both sides. It doesn't really matter. Fourth root of 0 is 0. So we have x squared plus 1 equals 0. X squared equals negative 1. That has no real roots because x is going to equal plus or minus the square root of negative 1. That doesn't actually work, so that would be imaginary. That's kind of nice for us. And 9x squared minus 6 equals 0. 9x squared equals 6. X squared equals 2/3. X equals plus or minus the square root of 2/3. Or x is about .82. So we've done all this. We have our actual critical points. So our critical points x equals 0, negative 1.41, positive 1.41, imaginary, we don't need those, positive 0.82, and negative 0.82. So then we draw a number line. Here's 0, negative 0.82, negative 1.41, positive 0.82, positive 1.41. Now I'm going to do the first derivative test. It's just the one I've always been partial to, but you are welcome to do the second derivative test. And I'm going to do this by picking a number in each of these intervals and plugging it into my derivative. So let's pick like negative 2, and you can pick any numbers. These are just ones I'm picking. Negative 1, negative 1/2, 1/2, 1, and 2. And we're going to plug all of these into our first derivative. Or dy dx. Let's see. So here is dy dx. So I have to plug all of those in. I'm going to go ahead and pause this and go do that in a computer or a calculator because otherwise this is going to take longer than I want to do. So I decided to go to Wolfram Alpha because I didn't want to type it in my calculator that many times. So I've typed in the actual derivative, and then I just say at x equals 2. So that means plug in x equals 2. And at x equals 2, I get 600,000. So that would be a positive. And so my derivative is going, or my function is increasing. Okay, and then it's simple enough to say, okay, that was, oh, oops, that was positive 2. Guess I should put it in the right spot. So over here at 2, it's increasing. Okay, let's try -2. At -2, I'm at -600,000, so I'll be going down, so I'm decreasing. At -1, I'm at 96, that's positive, so I'd be going up. At -1/2, that looks like a negative, so I'd be going down. Now, sometimes people get tired of checking all of these and they just say, okay, it's going to go every other one. But that's not true. You should always check every one, because you might get a circumstance, like maybe this one might change and be negative as well. Let's see. Nope, it's still positive. So we're going up. We'll check the 1. And we're negative, so my function is decreasing. So y itself is decreasing, then increasing, decreasing, increasing, decreasing, increasing. So just based on what that picture looks like, even though it did take me a long time to come up with this, if I'm going down and then up, that looks like it would be a min. If I go up and then down, that would be a max. Down and then up would be a min. Up and then down is a max. And down and then up is a min. So we have mins at x equals -1.41, 0, and 1.41. I think this problem, at least first step, told me to actually find the maximum. So the maximums are at x equals -0.82 and x equals 0.82. Now, if you look up here at our actual problem, it said type an ordered pair. Okay. So that means you need your actual y values. So to find the y value, plug x into y. To get y values for ordered pairs. So if x equals -0.82, then y is going to equal what? So I went up above, that didn't work, and I copied what y equals, just so I can see it here. So if x equals -0.82, y is going to equal -0.82 squared minus 2 to the power of 4 times -0.82 squared plus 1 to the power of 5. So I put this in and y is 40.64. And similarly, if x equals positive 0.82, then y is also going to be 40.64. And so you have two sets of coordinate pairs. So your maxes are going to be at -0.82, 40.64, and 0.82, 40.64. And so those are my maximums. If you wanted to find your minimums, the same things we had up here, we knew where our minimums were. You could just plug it into your y values, into your original y equation to get y values.